your surname is pronounced Lowe?
Yes, Lowe.
Okay.
Right.
So we'll get started.
Okay, sure, yeah.
Good afternoon, everyone. My name is Doug McAvoy. I'm Deputy Chair of the Centre for Clinical Change in Healthcare Research. It's a pleasure this afternoon to have with us Professor Murray Lowe, who is the Fulbright Distinguished Chair in Advanced Science and Technology from the George Washington University in Washington, D.C. He is, as I believe, the guest of the Defence DSTO Science and Technology Organisation. And I was this afternoon given a short bio of him, and also some of the topics that you potentially speak to us on, which range from analysis of precious artwork through to analysis of breast cancer. And that's quite a suite of talks you've got there, Murray. So I guess a number of us are intrigued by the tracking and image analysis that's probably going on shortly, at least, and presently in the Indian Ocean. So, and DSTO probably has got something to do with some of the technologies that are being used out there. But I'm sure Murray has been out there teaching them a few new tricks.
Well, it's mutual, actually.
And we look forward very much to what you've got to tell us about the infrared imaging for the detection of breast cancer this afternoon. So thanks very much, Murray.
Thank you. Nice to be here. Well, I appreciate the kind invitation to be here. It's really a pleasure, and I thought I'd start just. I know most of you know where we are, of course, but George Washington University is in Washington, D.C., out in our nation's capital. And the reason I put this slide up is that there are 14 universities in America that have either George or Washington in their name, and we get confused with most of them. So I wanted you to know who we aren't. Here's Washington, D.C., which, by the way, when it was created in the late 1700s, after the country was formed, it was a 10-mile square. So it was 100 square miles removed from Maryland on this side and Virginia on that side. And then early in the 1800s, Congress decided that because the Virginia side was a swamp and in other ways not very attractive, they gave this part back. So Virginia now has that, and the area between the Potomac River and the rest of the square is what is Washington today, about 60-some square miles. Anyway, so we're here very close to the White House, and 1 mile away from us is Georgetown University, so that's number one with whom we get confused. About 10 miles away in Virginia is George Mason University, and we get confused with them sometimes. Down here in Virginia is Washington and Lee. We don't get confused with them that often, but sometimes. And then in St. Louis is Washington University in St. Louis, and then out in Seattle is University of Washington. So we're none of those. We're the one closest to the White House. Well, what I'd like to talk about is how infrared can be used, we think, to do a good job of detecting breast tumors early. And what you're seeing here is a set of thermograms taken by this group in Florida. And one of the problems that we've discovered, and that has been the case for many, many years, is that thermography, that's a name that a lot of people give to it. I'm not sure that's the best name, but in any case, that thermography has been a very informal process. Radiologists don't practice it at the moment, at least in the United States. And the places that do practice it do it in a very empirical and not, in my opinion, very scientific way, unlike radiology as we think of it in most circumstances. And so what we set out to do was see if we could come up with a more rigorous basis for doing and for capturing and understanding thermal images. And so we wanted to start at the beginning. And there are many, many papers, of course, in the literature that have approached this. And so what we're doing, the approach that we've taken, I think you'll see is a bit different from many of the papers that are out there. Well, so start and you say, look, what's the goal? The goal is that on one hand, there's physiology and pathology in the breast. There are a lot of internal factors that are there under normal circumstances, and then tumors create some additional changes. There are the external factors. What's the shape of the breast? What's the environment in which we're looking at it? So together they constitute this physiology and pathology. On the other hand, we have a camera of some sort which is going to image the breast, and again, the reason, of course, that it's infrared is that we're all radiating infrared all the time in the 8 to 12 micron range, typically. That's where the peak of the energy is. So we have a camera sensitive in that range, and it's going to be recording, making a map of temperature. Well, how do we relate them? Well, if we had really good understanding of what's going on here and a bit of what's going on there, we could take those and construct a forward model. That is to say, we'd know what the shape is, we'd know what the thermal activities are due to these various processes, and we'd be able to combine them and create, to synthesize an image of what the temperature distribution on the surface of the breast would be. So that's the forward modeling case. The inverse case is the one that we're more typically going to be dealing with, because we're usually not going to know all these things. So what instead we do is record this image and then try to perform some sort of inverse modeling to infer some of these characteristics, and in particular those of the abnormality, from the image. And so that's the goal. Well, in previous studies, there weren't a lot of factors considered that we did, and for example, the question of deformation. In many cases, the breast is modeled as a hemisphere. Well, under certain circumstances, it might be, but if you have a woman sitting in a chair, it's almost surely not hemispherical, and the question of how those changes in the physical shape would affect the thermal image weren't addressed. At least we couldn't find any work that dealt with that. And then the second aspect that we looked at is the question of dynamic measurements. That is to say, if you could cool the breast and let it then re-warm to body temperature, or warm the breast and let it cool down to body temperature, could you learn anything? And it turns out that our models at least indicate that we can. And so then the question is that other work mostly looked at the forward problem, and there was not in those forward models the specification of individual properties, how to account for a person's individual physiology. And those also didn't specifically address the tumor detection problem. So what we're interested in is to combine the thermal and the elastic modeling, that is to say the deformation, to look at the dynamic characteristics of the problem, and also to then approach this inverse problem directly. And so what we're going to be interested in, again, is we'll have a general model, but we want to incorporate as much as we can about the individual person into that model, and thus to improve this estimation for what we call tumor-induced thermal contrast. In any image, almost always what we're concerned about is contrast, the difference in intensity between an object of interest and the background. And what we'd like to do, of course, is increase the contrast between a tumor and the tissue around it. So let's take a look briefly at some of the modeling that we've done. We can use finite element analysis, finite element modeling, and we can use two kinds. One, the same sorts of modeling approaches, the finite element approaches, can be used to model both the deformation, in this case under gravity, and also the thermal characteristics that we would construct based on knowledge of the physiology, and soon, as we'll see, also to include the tumor. So these two steps of modeling are what we're interested in doing for the first part of our work. And if you ask, well, what's the anatomy of the breast typically? there are at least three kinds of tissue: the glandular, the fat, and the skin, and the chest wall, of course, supporting this. And one can then model this. We did as four hemispherical shells initially, and with thicknesses as indicated here. And then use the finite element modeling with this as the starting point, and with the physical characteristics of the tissue obviously included in the finite element modeling. And so one can then construct this, then apply gravity, and you can, with the finite element model, get a new view of what the breast would look like under those conditions. So this was the first step. Take characteristics of the tissue, use those in our finite element modeling, and deform with gravity. So we can then quantify those displacements, and you can go from inferior to superior, top to bottom, left to right, and posterior to anterior, and characterize those displacements. The mean values and the standard deviations are shown. And so we now have, and these are the changes, these are the deltas, if you will, of position. And you can see that it's far greater inferior to superior compared to left to right and posterior to anterior. So those are the deformations from this hemispherical model. And so already we're getting some useful information that we then will incorporate into our that will then enter our thermal model. Well, there are a number of models for thermal behavior, and one can actually compute the changes in temperature at various positions to use in our finite element model based on thermal conductivity. The characteristics of the tissue are known. We have some estimate of blood perfusion in the tissue due to the vascular nature. And in addition, we're generating heat from the metabolism of the body. And so then we'll have boundary conditions to impose at the breast-chest surface and at the outer surface, the ambient temperature. And we can then embed these in a thermal model, taking into account some thermal loading and thermal characteristics of the tissue itself. And if we do that, we then can ask, okay, let's model a breast with and without the gravity-induced deformation. And so in the no gravity case, you have this model incorporating all those quantities that you saw before, and this would be a cross-section through it. And you then, so this is then absolute temperature. You now can let gravity take charge and deform the tissue, and what you see is now a definite difference. And so this is now delta T. This is absolute temperature. This is change in temperature. And what you see, perhaps surprisingly, is a warmer section on top and a cooler section on bottom. And this has to do with the changes in the vascular structure as a result of that deformation. And so already we're learning something about this that is important, because if you said, look, what we're looking for is a warm region, and let me back up for a moment just to talk about why we would have any hope that this would work. When a tumor grows, there is angiogenesis. New blood vessels are created. And those new blood vessels are there to nourish the tumor, and they cause a local rise in temperature. So that's, after all, what we're seeking. The goal is to see if we can detect that increase in temperature that's due to the formation of the tumor. Well, if you didn't know that deformation in and of itself caused a temperature increase or a temperature asymmetry here compared to here, you might be inclined to conclude, oh, there's a problem because there's this temperature increase up here, when in fact all that's due to is the deformation. There's not a tumor present in this model. So it's important to be aware of the intrinsic properties that are going on as a result just of gravity. So again, if you're going to image a woman sitting in a chair, you don't have a hemisphere. You've got a deformed surface which leads to asymmetries in temperature. Well, now what happens if you introduce a tumor into this, into the model? And so you can embed a simulated tumor either off-axis or on-axis, and there are various characteristics that I won't get into in detail, but certainly it is stiffer. A tumor is stiffer than the surrounding tissue. The thermal properties are a bit different. The blood perfusion rate is a whole lot greater, and the metabolic heat generation is typically greater. So one would expect that with the thermal properties of the tumor being appreciably different from either of the major two kinds of tissue in which it would be embedded, that we ought to be able to take advantage of that for the detection using a thermal process. So let's do that. So here is absolute temperature as a function of both the diameter and the position of the tumor. And what we have, this is the diameter of the tumor and the depth that it will, at which it's located. Let me just check to make sure I have the right notation here. Right, so what we have is the tumor of at various depths, 6, 10, 14, 18, 22, and 26 millimeters into the breast. These are the absolute temperatures. Suppose we now subtract the background, the non-tumorous breast image, from this image. We then have a set of difference images. And that's this delta T then is what we're seeing. And clearly the deeper it gets into the breast, the less evident it is on our image. It's there, but it's certainly not as apparent here as it was there when it was much shallower. So what we have then is a question of, again, this is all modeling results. This is not yet actual data. So the modeling results indicate that, yes, it's evident, but we certainly would like to be able to have higher contrast if possible. Now, let's combine these. And so we are comparing now tumor size increasing that way and tumor depth increasing that way. And this is the maximum delta T. And again, what we want is, all things being equal, we'd like to have the maximum possible delta T so that it's evident to our thermal imaging camera. And so you can see the delta T's here at the high end are about almost 2 degrees C, maybe 1.5 degrees C in the on-axis case, and in the off-axis case, under some conditions, it could be even greater. And of course, it's great. The temperature difference is greater when the tumor is shallow than when it's deep. And as it gets deeper, this curve falls down until there's almost no thermal difference present. So the deeper it gets and the smaller it is, obviously, intuitively, the more difficult it's going to be to see in terms of temperature difference. So again, all of this is the modeled results. But what it's telling us is, yes, if the model is about right, that we ought to be able to detect tumors up to some depth, perhaps 20 millimeters, depending, and for various sizes. So then the question was, all right, is there any benefit to now making this process dynamic? And by that I mean changing the external conditions. Everything that you've seen so far is under static external thermal conditions. And so I won't go through all the details, but it is possible to incorporate time into this process and to then recursively solve this equation to come up with what the differences ought to be as a function of changing the external temperature. And so we define two quantities. One is called di star, which is our deformation-induced surface temperature alteration ratio. That is to say, due only to gravity or to some other process changing the shape of the breast. The second is are the changes induced by the presence of a tumor. Again, because it's there, because it has its own high metabolism, and because it has, because it's generating heat, it will create some changes in the surface all by itself. And so what we defined then was a set of quantities. We took the standard deviation, we computed the delta T, the change in temperature between the breast without gravity and the breast with gravity. That gave us these quantities. We take the standard deviation of the temperature differences across the breast, divide by the mean, so we get some sort of coefficient of variation. And we can do a similar sort of thing when the tumor is present. It's a simple measure, and the question was, would it tell us anything about the dynamic behavior of the breast? And so here's what we did. We computed both of these measures as a function of time. And what was changing was the external temperature. So we cooled the breast to 20 degrees C in simulation, and then let it rewarm up to 25. So that was considered the baseline temperature. And we did this for 3 starting points. That is, we went from 25 to 10 to 15 and to 20, and let the breast rewarm. And what we saw as time went by were these characteristic curves of this di-star, again, the standard deviation divided by the mean for the whole surface as a function of time. We then, so this was the recovery, and then we went from minus 10. Sorry, this was when we cooled it down. We went from minus 20, from 25 to 10 to 15 and to 20. So this was the cooling. So we started at 25, we cooled it down to 10 degrees in the case of the red curve, to 15 in the case of the green, and to 20 in the case of the blue. And if we followed that as it cooled down to its destination temperature, these are the curves we got. We then did the reverse. We said, okay, start at 10 degrees. Cool it to 10 degrees, let it stabilize, and then let it rewarm to 25, from 10, from 15, and from 20. And so we got these characteristic curves of the recovery. Now, what happens if we embed a tumor? If we embed a tumor in this mathematical model and do the same sort of thing, so we're going to have cold stress, that is to say, cool it down from 25 to 10 or 15 or 20. Let's see what the curve looks like. And the curves are quite different from these. Just the reverse, almost. And so this is a very evident kind of phenomenon. And when we did the same in the other direction, that is to say, cool the breast and then let it rewarm with the tumor present, we got curves that look like this. Again, the opposite behavior from what we had here. So the question then is, again, all of this is simulation. All of this is simulation. The question is, with a tumor at various depths and of various sizes, might we be able to see it more clearly, with more contrast, if we were able to either to cool the breast or to warm the breast, as the case may be, and let it then return to body temperature. And so we then can answer that again in simulation in the following way. In simulation, we embedded the tumor at various depths, and we computed this cold stress that you saw a moment ago, right here, now in the presence of a tumor. And what we see is that these curves are substantially different at the different depths, but they all exhibit this same characteristic peaking behavior. And so if you look back at the case of no tumor, the di-star situation, and you compare these curves to either these or these, you certainly see a difference. So the tumor is making an appreciable difference in the phenomenon of the distribution of temperature over the breast is making a substantial change that's evident quite readily when compared to the no tumor case. And this is true both in the cold stress and in the thermal recovery cases. So the point is that, again, in simulation, it appears that if we could get a subject to go along with this, and we could either cool or warm the breast slightly, and then monitor its change in temperature over time as it returns to equilibrium, that we would have apparently a good way to detect the presence of a tumor quite reliably as compared to the no tumor case. And so this is a very encouraging idea. It has not yet been, I'll tell you what the story is with experiments in a moment. But this was the very interesting idea. Li Zhang, my doctoral student, was greatly responsible for this, and turns out to have worked very well, again, in theory. So let's return again to this question of forward versus the inverse problem. Again, if you know everything, you could construct a model and go forward and predict what the surface temperature would be, the distribution across the surface of the breast. But we don't have that in virtually all cases. What we have is the reverse. We have an image that shows temperature all across the breast, and we want to go the other way. So what is it that we could do to make this process even better? Well, just to compare, again, in the forward case, we've got numerical robustness, and there is a unique solution. We're plugging all these data into a model, and we get a value for a given position on the breast. But it requires knowledge of these individual properties. You have to know mass, you have to know the distribution of vessels, ideally, and on and on and on. In the inverse case, we've got a thermogram, but we have numerical instability. There is, in general, not a unique solution. When you go the other way, there could be many possible solutions that would have yielded what you saw in the image. So let's introduce some constraints to try to bound this problem a little further. And so we have several properties that we're interested in here. And so the K and omega 0 and Q 0 that we saw earlier, the heat capacity and these other characteristics. And so we've got these thermal properties that we're interested in that vary from person to person. So what we asked was the following. A given person appears with her specific characteristics, K, omega, and Q. They are related somehow to standard reference values of these. If you were to take an average over a population, you could come up with average values of these three thermal characteristics. So the question is, if we could find scale factors that would relate the average values that we could find, say, in the literature, to the person standing before us, then we could make a much more accurate calculation of what to expect. And so how to do that? Well, one way is the following. We take a thermogram, a thermal image. Noise, of course, gets added. So here's our observed tumorous thermogram. We then ask, here's a breast model, a mathematical model. And we have the elastic properties, let's suppose, are fixed. We're trying to estimate the thermal properties. And so what we're going to do is compare the model, the thermogram, that results from this model that's based, at least initially, on average properties. And we're going to compare our observed tumorous thermogram, imagine a real case, to a simulated thermogram of a normal person. And we're going to modify the thermal properties until this difference is minimized. Well, now, what are we doing here? This real thermogram, rather, of an actual person, is having subtracted from it a model of a non-tumorous thermogram. But the goal is to understand the thermal properties of this person. So what we're doing is using an optimization procedure to minimize this difference so that what we're subtracting is as close as we can get to a tumor-free thermogram for that person. That is to say, we're adjusting K and omega and Q, those three parameters, so that we're making this the best possible fit without a tumor to this one that has a tumor. And the idea then is that this would give us a reasonable measure for this tumor-induced thermal contrast that we saw before. Now, this is one way to do it. There's another way to do it. If you look at the statistics for breast cancer and you ask in how many people, what fraction of people who have breast cancer have it on both sides, it turns out to be between 2 and 4%. So let's assume for the moment that if there is breast cancer, it's on only one side. If that's true, then the other side serves as a control. And so we can estimate, if we wanted to, the thermal properties, the K and omega and Q, from a person herself. So we wouldn't necessarily have to use this. So we have at least two ways to go at this question of the individualization of the parameters for the thermogram calculations. And I think this is going to be essential from some other points of view that I'll tell you about in just a moment. So again, two ways to go at this. One is just an optimization technique where we're simulating a non-tumorous thermogram that has the characteristics of this woman. And in the other case, we actually measure and use those values. So then the question is, well, what about this question of noise? There's always going to be uncertainty in our measurements, and the question is, if we consider two of our thermal characteristics, in this case, blood perfusion, the omega, and Q, which was the heat generation rate, and we ask, okay, what happens if the measurement that we are making of our quantities is imperfect, which it will be, of course. And so we can express this as a signal-to-noise ratio. The higher the signal-to-noise ratio is, the less noisy, the better our images are. And so as the signal-to-noise ratio increases, we get closer and closer to better values, of course, the green, and the blue values and the red are the outlying ones. But the fact is that we can certainly give an overall average. By averaging the values, we can nevertheless come close to our correct value. So what we're saying is that even though we may have a fair amount of noise, we can expect that averaging over our entire breast image will give us pretty good estimates of the Q and the omega. So now let's see what this leads to. Taking typical values for our multipliers for a real person, we can ask the following question. Here's a 16 millimeter tumor at a depth of 10 millimeters, and here is the temperature that we record. And we then ask, okay, what is delta T if I use the normal, the reference parameters? So I use the average for some population, not this specific one's parameters. If I do that and modify and compute using the expressions you saw before, and now find my delta T, the change in T based on those average parameters from the normal value, this is what I get, which is okay, but not great. This is truth. If we knew perfectly everything there was to know about the thermal parameters, this is the image we would get if we knew perfectly. So the correlation coefficient was only 0.32 between this image based on average parameters and this image based on the perfect knowledge. Well, if we were to correct this using the optimization procedure you saw a few slides before, this one, if we were to do this nonlinear optimization and estimate those thermal properties, we would get a plot that looks like this, which now has correlation coefficient of 0.99 with perfect knowledge, with the perfect knowledge case. So this gave us confidence that our optimization procedure would be useful. Again, this is all in simulation, so there's still a lot to do before we get to a real tool. But at least this was encouraging and gave us the basis that we had been seeking for now going further. So let's take a look at this correlation coefficient versus tumor depth. Again, we're computing the correlation between a corrected image, corrected based on the optimization procedure you saw, the correlation between it and truth. And so what we see is that for various sizes, the correction factor creates a very strong correlation between the corrected and the truth. The uncorrected ones, depending on depth, are very poor and almost unuseful. So again, and this is for the relatively high signal-to-noise ratio case, not much noise present. So let's go on and see where this leads. What we've got at this point is a set of techniques for doing modeling. In the static case, we can understand what deformation does when gravity is involved, but we have poor sensitivity on the deeper tumors. If we were to now use our dynamic approach, where we allow tumor and deformation over time to be quantified, we can get a real understanding of the presence of deeper tumors. The inverse modeling that I showed, the idea of being able to estimate individual parameters, is going to help, I think, as well. The improved, this thermal contrast will be estimated and estimatable for deeper tumors. So we like to think of it as bringing science to thermography from sort of a very crude and empirical set of techniques that have been used so far. And the next step is to actually take some data. And so we've been fortunate to have loaned to us a very high precision infrared camera that has resolution of about a 20th of a degree C in temperature and about a millimeter spatially, so that we can take an image in one sitting, a few seconds acquisition time, to be able to take data. One of the great hopeful characteristics of this approach is that unlike mammography, which involves compression, and women generally hate it, and which involves radiation, this is non-contact and there is no radiation, and it takes a few seconds to acquire the image. We are certainly not expecting any time, probably in our lifetimes, for this to replace mammography. But we think it will have the benefit of being able to be an adjunct to mammography that will perhaps increase the overall sensitivity. We're about to submit an IRB to allow us to do the study. We'll get volunteers. Our director of the breast clinic is very enthusiastic and promises to recruit people who are willing to do this. And we will get truth, as it were, or as close to truth as we can get, from mammography and in some cases biopsy. One of the interesting questions and problems here is that of false positives. Suppose something on the thermal image looks suspicious, although nobody yet knows what suspicious really means, but we think we might, but no data. But if here's a region that we think might be a tumor, and there's nothing on the mammogram, then is this a false positive? Well, certainly at that moment in time, it probably would be. But if we follow that patient, that subject, for several years, we would be able to see whether what we had detected or thought we had detected at a given point, in fact, was going to become something more visible in a year or two. So one of the concerns as we're thinking about the design of all this pilot study is, whether and how to treat this question of false positives. And of course, the most conservative way is just to treat it as a false positive and not do anything else. But we're hoping that at least some of these of our early volunteers will be able to come back for future studies, and that we might get data in the long term. So the next step after the pilot study will be to go and see if we can get funding to carry this out on a larger scale and see whether this has real benefit. So I'd like to thank again the Australian American Fulbright Commission and DSTO, through whose generosity I've been able to come to Australia, and to thank you for your attention. And those who are interested in getting in touch with me, here's my email address. I'll be at DSTO through the end of June if you want to get me locally, and I'd be happy to try to answer any questions. Thank you.
What you're trying to do is really commendable in the sense that you're trying to design a proper model on which you're going to base, compare data to which compute in order to make some kind of decision. I won't call it diagnostics because it's screening, right? So, but anyway, to make a decision. If you compare it to mammography, there's lots of people who have worked on that kind of thing for a long time, and the approach to designing a good enough model to model the physiology and the acquisition process and everything else, so that you actually have a model that's so useful that you can predict the manifestation and answer in the image, and thus base a decision on callback or not on that. It's proved to be tremendously difficult when people have made progress. Whereas most of the work that's done on sort of assessing mammogram via technology is a machine learning approach, right? Where you get lots of examples of cancer present, cancer non-present, and you learn, you extract features, you do image analysis, and then you learn the differences. That's sort of a brain dead way compared to what you're doing. But history tells us that your approach would be best, but it's extremely difficult. So, can you comment on that at all? Would somebody like to do a machine learning attempt?
Well, we actually have two paths that we're planning to pursue. One is the formal approach that we've got here. The second is, once we have the data, and again, assuming that if there's cancer on one side, there isn't on the other, then we ought to be able to do a lot as far as machine learning is concerned. One of the concerns, for example, is how does the vascularity, the natural vascularity of the tissue, affect the images? And so one could say, well, if I have an image of the breast that is cancer-free, couldn't the vascularity there be used somehow to help prevent confusion on the other side? They're not mirror images, of course, but the way to characterize the vasculature is an interesting question, texture or whatever, if that turns out to be a problem. But and in any case, the machine learning approach, maybe not completely brain dead, but would nevertheless be, yeah. But the machine learning idea to simply use the data that we will have is absolutely something we want to do. Sure.
What about the computational complexity of nonlinear optimization? Is it going to be done in real time, or are you going to do it?
Well, it wouldn't have to be done in real time. I mean, we're going to take the data, and we could come back tomorrow. Or, it doesn't have to be done instantly, and especially in the early days, because it's not even approximately a clinical tool, so we're really just experimenting and getting data. And then we'll see how well that works and what refinements might be made to simplify it and so on. Yeah. Yes.
system. And you're very prone to false positives, right?
Yes.
A large dimensional feature space, degree optimization, lots of local minima, and to get credible results, and probably the null space for the inverse problem is large. You mentioned that yourself, right? And on top of that, you have noise. So it's very difficult to get these to work. I mean, you should try, of course, but that approach is.
Well, right, but I think, it's not as if we don't have a reasonable starting point, because I don't know off the top of my head what the variation in those three parameters is across a population, but it's not so great as to make our starting point meaningless.
Is there also spatial differences in this parameter?
There probably are. We assumed homogeneity here. And that's certainly something that could affect things, that's for sure. The question is whether the intra-person variation is bigger than the inter, and remains to be seen.
Also, do you have any information about at what stage of the cancer the thermal properties become?
No. That would be wonderful to have. We have looked a lot for that kind of data and haven't been able to find it. It's interesting, just as a side comment, you may know that when tumors grow, the vessels that develop are not fully competent vessels. They're leaky, and they also lack the thermal behavior that normal vessels have. If you stick your hand in cold water, the vessels in your hand shrink. They contract because your body is trying to protect the rest of itself by letting the hand die, as it were. So this contraction of the vessels occurs normally. Well, one of the reasons that we're interested in this thermal idea is that if we could cool the breast a bit, then the normal vessels are going to shrink, are going to contract. The tumorous vessels, if present, will not. So the contrast is being increased by this process, leaving everything else aside. The poor workings of the tumorous vessels mean that the blood flow continues, whereas the healthy tissue, it diminishes. So the difference in temperature should grow. Now, when we tried to investigate this question of why it is that these vessels do this, everyone says, yeah, that happens, but we could not find a paper in the literature that gave the fundamental explanation of that behavior. So there's a lot still to be learned.
Do you see a time when you'll have sufficient spatial resolution in this to be able to direct a biopsy into a tumor, or is it just that you know somewhere in there's a tumor?
Well, that would be in the future, some sort of 3D rotation. But, that would be certainly a very great goal, sure.
One of the reasons that infrared has always been attractive is, as you said, women don't like breast compression. But I just wonder how women will compare the breast compression to having your breast reduced to 10 degrees.
Well, that's right. And there are all sorts of issues there. There was a company in the U.S. that actually had an FDA-approved thermal imaging system that involved, I think they blew cold air across the breast, and it was not accepted, but I don't know for what reasons. I don't know that women didn't like it. But eventually the FDA withdrew its approval of this. And I don't know, all of that is, I don't know all the story. So there's a lot of opportunity, I think, if it's done in the right way. But the cooling issue, I don't know. Would women be happy with the trade-off? I don't know.
Intrigued by the change in temperature with the gravitational distortion of the breast between the top and the bottom. you say in layman's terms what that was primarily due to? Was that
I
change in the blood flow?
yes, mostly change in blood flow.
Okay.
Right. Everything else was small compared to that. So it's just increased flow
To the
to the
non-dependent portion of the breath.
yes.
I come from lung physiology, and the early studies, in fact all studies have shown that the gravitational effect is to increase blood flow at the base of the lungs.
Right. Right.
So
Right.
what is going on there?
Well, when we modeled the vasculature and the blood flow, we used a homogeneous model again, and I think it's a question of that there may be some compression of the vessels when on the underside, so the blood flow is diminished slightly. I think that's probably it. That there is some reduction of flow.
Tissue pressure.
Yeah,
External
yeah.
blood.
And again, you have these three kinds of tissue interacting, and it's with different stiffnesses.
Further questions? Well, thank you very much, Mark.
Yes, my
Everyone
pleasure.
was very good.
Thank you.
Okay, I would just like in closing to thank you very much, Murray, and again, and this is a mature to perfection wine from
Oh,
South
my.
Australia. So on behalf
Ah,
of the Clinical Change
lovely.
Group, thank you very much for your time.
Thank you.
Yeah.
Thanks very much. We'll enjoy it.
So do you interact very much with the clinicians at George Washington?
Well, depending on the